Okay, you're ready to go.
Okay, great. So welcome back, everyone. So we have the second quantum session today, and it's going to be a mostly online session. And the first talk is about secure software leasing from standard assumptions. And the paper is by Fuyuki Kitagawa, Ryo Nishimaki, Takashi Yamakawa, and Ryo is going to give the talk.
Thank you for the introduction. I'm going to talk about secure software leasing. This is a joint work with Fuyuki Kitagawa and Takashi Yamakawa from NTT. Secure software leasing is a quantum cryptographic primitive. There are a lessor who has a software and a lessee. A central authority generates a common reference string. The lessor generates a protected software by using a secret key. Then the lessor sends it to the lessee. The lessee can run the software on a legitimate platform. That is, they can get an output for an input. At some point, the lessee returns this software to the lessor. Then the lessor checks whether the returned software is a valid leased software or not. After the lessee returns the leased software, they cannot run the software anymore. That is, leased software must be a quantum state since we can easily copy classical information. There are two security notions for secure software leasing. One is finite term security. In this security game, an adversary receives the protected software. Then the adversary tries to generate possibly entangled bipartite states. Both of them can be used to run the leased software. The adversary sends one state to the lessor as a returned software and uses the other one to run the leased software. Finite term security guarantees the returned software is not valid, or the adversary cannot run the leased software on the legitimate platform anymore. Here, the adversary is forced to run software by an honest evaluation algorithm. The other notion is infinite term security. This is stronger than finite term security. In this security game, the adversary also tries to generate possibly entangled bipartite states. Then the adversary tries to use both states to run the leased software on the legitimate platform. Infinite term security guarantees the adversary cannot use either of the two states to run the leased software. This is our result and comparison. Anand and Lapreka presented the notion of secure software leasing and instantiated it for subclass of evasive functions by using public key quantum money and the LW assumption against quantum adversaries. Their scheme achieves infinite term security. Some concurrent and independent works of our work improved the assumptions, but the function class is limited to subclass of evasive functions. Aronson et al. Achieved secure software leasing for broader function classes, but they still need public key quantum money. Ours is the first secure software leasing for broader function classes from standard assumptions. In our paper, we give constructions for pseudorandom functions and subclass of evasive functions, but our construction can support public key encryption and signature by combining the technique by Aronson et al. Our construction is based on the clean framework using software watermarking. We can instantiate the watermarking part with standard assumptions. Aronson et al. Concurrently and independently presented a similar technique based on watermarking. We note that some works achieve security where pirate software is not forced to run by honest evaluation algorithms. Lastly, our construction can be achieved only with classical communication. That is, we do not need to send quantum states. This is our result. Now, our scheme is based on the scheme by Anans and Laplace, so I review it. Software is modeled as a classical circuit. We somehow generate a protected circuit in the classical way and connect it to a public key quantum money. When we return the leased software to the lessor checks the quantum money is valid. Then the lessor also checks the protected circuit part is correctly connected to the quantum money. If both are valid, the returned software is valid. When we run the leased software on a legitimate platform, the platform does the same check as the lessor. It checks both the quantum money and the connected part. The crucial observation here is the lessor can use their secret key for checking returned software, while we need a public key to run the leased software on a legitimate platform. We found that we do not need the full power of public key quantum money for finite term security. So instead of public key quantum money, we use two-tier quantum lightning, which we introduced in this work. This is a relaxation of quantum lightning. In two-tier quantum lightning, an authority generates a public key and a secret key. Anyone who has a public key can generate a vault as quantum lightning. There are two types of verification in two-tier quantum lightning. One is full verification, which needs a secret key. The other one is semi-verification, which needs a public key. So anyone can execute semi-verification. However, only the authority can execute full verification. In the security game, the adversary generates potentially entangled two quantum states as quantum lightning. In two-tier unclonability game, one quantum state is checked by full verification using the secret key. The other quantum state is checked by semi-verification using the public key. Two-tier unclonability guarantees one of the two states with the same serial number is invalid. We can construct secure software releasing by using two-tier quantum lightning instead of public key quantum money. We also use software watermarking for the circuit protection part. A lessor generates a vault and serial number and embeds the serial number and the public key of two-tier quantum lightning into software by watermarking. So the software is connected to the vault. When a software is returned, the lessor extracts the embedded public key and serial number and checks the vault part by full verification with the secret key. When a lessee runs software, they extract the embedded public key and serial number and checks the vault part by semi-verification with the public key. Precisely speaking, we need MAC to formally prove the security of our construction, but I omit it for simplicity in this talk. We can prove the finite term security of our construction by using two-tier unclonability and unremovability of watermarking. The adversary generates two states. One is checked by the lessor and the other one is run on a legitimate platform. Suppose the first one is valid under full verification and the second one is valid under semi-verification. We consider two cases. First, if the extracted public keys are the same in two states, the adversary breaks two-tier unclonability. In the second case, if the extracted public keys are different, the adversary breaks unremovability of watermarking, since valid software must preserve the functionality of the original software. Note that this argument is oversimplified since we omit the MAC part from this intuition. This is the summary of our work. All building blocks can be constructed from the QLW assumption. We can also achieve secure software releasing with classical communication. However, I omitted them in this talk. Please see the video or paper for the details. That's it. Thank you.
Thanks a lot, Ray, for the talk. So I think we're running a little bit out of time, so we can have the questions for Ray towards the end, unless someone has a quick question, while the next speaker, Omri, sets up. So Ray, we can get to the questions for your talk towards the end of the talk, towards the end of the session. So Ray,
Okay, so I was just updating that Omri unfortunately called me 30 minutes ago. He had an accident.
So
Anyhow,
do you think we could have your talk right now, the classical binding for quantum commitments, and get to this talk towards the end of the session in that case?
So what we're going to do anyhow, because he's not going to get here, is in the hospital. Since I didn't have any time to prepare anything, there's a talk by Michael from QCrypt, a 5-minute talk, and we're going to broadcast it right now. And we already checked that it works, so no worries.
I hope Omri is not serious.
Me too. But I spoke with him on the phone, so he's conscious. He's sort of walking or limping, I guess. But he has to get a few tests done to know that really everything is fine. So get well from here.
Get well from everyone at PCC, I would say.
Yeah, so let me play the video and I'll be happy to answer questions afterwards.
So hi, everybody. I'm Michael, and I represent the following work, which is a joint work with Neil Bitansky and Omri. All of us are from Tel Aviv. So what we have done, we started to consider the notion of quantum resettable soundness. I don't have that much time to recap all what was done in the classical notion, but what we do is we consider resetting attacks where the prover has quantum oracle access to the verifier, and he needs to cheat the verifier at some session. The motivation that we have for considering such a notion is twofold. The first one is to achieve such a security guarantee, as was done in the classical case. And as Takashi has mentioned before me, the notion of black box zero knowledge is indeed very important to understand. And we hope that, as in the classical case, understanding more about quantum resettable soundness will help us understand more about the limitation of post-quantum black box zero knowledge. Again, as Takashi mentioned, we show analog results to their regarding free message and constant round public coin. We show that there cannot be any black box zero knowledge protocol that is as those described here. And we achieve this by observing that, as in the classical case, post-quantum black box zero knowledge and resettable soundness cannot coexist together. And using this observation, we use measure and reprogram techniques to transform, for example, free message protocols into classical resettably sound ones. And as such, there cannot be post-quantum and resettably sound zero knowledge with free messages or public coin. This is the first result we achieve in the paper. The second result is on the positive side. We show how to construct a post-quantum resettably sound zero knowledge protocol for any language NMP. Our protocol assumes the hardness of quantum learning with errors and quantum polymorphic encryption. The construction is constant round. Again, zero knowledge is post-quantum, which means it holds against quantum verifiers, malicious quantum verifiers. And just to give a little taste, our protocol indeed begins from the protocol of constant round zero knowledge, which is indeed non-black box from Bitansky-Shmueli, but the protocol as is not resettably sound even classically. And we need to first try to think how to transform it into a classical resettably sound protocol via the Lapidot-Shamir trapdoor paradigm, and then try to solve all the technical difficulties that arise from the fact that we're dealing now with quantum adversaries and not classical ones. And the last result we show is again an analog of the classical result, which shows a connection between resettable soundness and a quantum virtual black box obfuscation. We show that any resettably sound zero knowledge protocol for NP and some kind of hardness in the post-quantum world, for example, one-way functions, implies that virtual black box obfuscation is impossible. This, with the construction of the protocol, is an analog result to the impossibility results that are mentioned here. And also, I'd like to mention that if we were ever to construct a better, weaker assumption protocol, which is resettably sound, we can immediately imply that quantum virtual black box obfuscation is indeed impossible. And as such, trying to build, for example, a public coin constant round non-black box protocol will be as difficult as showing that quantum virtual black box obfuscation is impossible. since we can transform it to resettable sound, resettably sound protocol, giving our compilers that we have discussed in the first result. So this is what I've
Okay, yeah, this was pretty fast. I'll be happy to answer questions now or later, whatever the format is.
First of all, thanks a lot, Nir, for just taking care of that. It would have been totally okay if we could have sort of had this talk later, but yeah, thanks a lot. And yeah, best wishes to Omri from everyone at TCC. And any questions from the audience, or I don't think there are any questions on the chat right now. And maybe I can ask a quick question. So can you expand on the last part, that these better protocols will imply better obfuscation schemes? You mean quantum obfuscation schemes for quantum circuits?
Right, yeah. So no, not for quantum circuits. So we're talking about quantum obfuscation of classical circuits.
Quantum,
okay, so to answer your question, whether quantum gives you more power, maybe you can expect you can get, for example, virtual black box for classical circuits, but using a quantum state. So your obfuscation is going to be a quantum state. And there are impossibility results for that from the past year, actually a couple of those. And they all seem to rely on somewhat strong assumptions, for example, fully homomorphic encryption. And it's not clear whether this is inherent, right? Like in the classical setting, we have unconditional impossibility results. And really sort of like the main engine there is one-way functions. So basically, like the basic question is, can you show impossibility of obfuscation using quantum, okay, of like obfuscation through a quantum procedure based on weaker assumption, based on one-way functions, or perhaps even unconditionally. And we point out that through this connection to resettable soundness, you might be able to get like a different path toward this this question. In fact, in the classical setting, you can instantiate this path, but in the quantum setting, at least for now, we don't know how to construct like things like let's say constant round public coin, zero knowledge, and stuff like that. If you manage to do that, and naturally it won't involve fully homomorphic encryption, which sort of automatically gives you secret key protocols, then we would also vicariously get stronger impossibility results.
Okay, okay, I see, I understand now. I thought that you were hinting that there might be better constructions for obfuscation schemes from sort of these new protocols. So you're saying no, it's the opposite.
No, it's more bad news. It's like
okay.
Yeah, but from weaker assumptions.
Okay. Thanks a lot, Nir, and best wishes to Omri. So let's move on to the third talk of the session, and Chipang is going to sort of kick the talk. Chipang, could you please share your slides? And the paper is on unifying pre-sampling via concentration bounds. And the work is by Xiao Guo, Qian Li, Chipeng Liu, Jiapeng Zhang, and please rectify me in case I mispronounce anyone's names, Chipeng.
Yes, thanks for the introduction. Yeah.
I don't think we can see your slides yet, could you?
Okay, yes, yeah, I'm still working on that. Okay, can you see that?
Yeah, perfect.
Okay, great. Okay, yes, thanks for the introduction. And the work is about the unifying pre-sampling via concentration bounds. So, okay, let's start. Okay. So we start by looking at a famous example of practical hash function, SHA-3. And for this function, the key building block is the function in the picture. The function seems very random and achieves pretty good performance in practice. But however, it is very hard to analyze, even for the most fundamental properties like collision resistance and one-wayness. So to deal with the difficulty in analyzing security, Belair and Rogge observed that random oracle captures most real-world attacks, and the proofs are much simpler. But however, security bounds in idealized models, like a random oracle model, provide an essential and heuristic justification and guidelines for their security in the standard models. But however, traditional idealized model failed to capture pre-processing attacks. The obtained bounds in idealized models are inaccurate or not applicable at all once preprocessing is allowed. And one famous example is pre-image finding. Well, when no preprocessing is allowed, it is easy to see that it requires roughly n queries to invert the image. But when preprocessing is allowed, the query goes down to n to the 2 seconds. So let's look at the formal definition of idealized models with preprocessing. So, when the adversary in the random oracle model is allowed to do preprocessing, we call such model auxiliary input random oracle model, or AI-ROM. There are 2 phases in the model. The first one is called an offline phase. There's an unbounded adversary can arbitrarily interact with the random oracle and making unbounded queries. At the end of the day, it produces a piece of advice of length at most s. And then in the online phase, another algorithm tries to win a security game. It gets advice from the offline phase and a challenge. And then it makes at most t queries, and the goal is to output a valid answer. So the reason to think about this offline procedure is because it captures the more realistic attacks, or in other words, the non-uniform attacks. And another reason is that usually it is crucial to answer online queries more efficiently, comparing to more efficiently. So for example, a hacker needs to respond to a server in a short period of time. The offline phase is allowed to take quite a while, because hash function is public known and everybody could spend a lot of time analyzing that function. So therefore, we define the security in the AI-ROM, which is simply the security against S bits of advice and T queries. Although the model captures the more realistic attacks, it is usually more difficult to work with, especially to prove its ST security. So there are a couple of techniques for analyzing security in the AI-ROM, and as you may tell from the title, in this talk, we will focusing on pre-sampling, which gives a simple and intuitive analysis. So the intuition behind pre-sampling technique is that although the advice can be an arbitrary function of the random oracle, for now, let us assume it is well structured. In other words, it only stores as pairs of input and outputs of the random oracle. And therefore, for an online adversary, it only knows these fixed coordinates, but nothing else. And therefore, the security is easy to analyze as long as the challenge avoids these fixed coordinates. And informally, pre-sampling theorem says that the advantage of any complicated advice is at most the advantage of some longer but well-structured advice. And let's look at the same more formally. So we first define the Bitfixing model. Well, a random oracle is sampled as follows. First, the outputs are arbitrarily fixed on p coordinates by the attacker. And then the remaining coordinates are sampled by the challenger or by the random oracle. And the pre-sampling theorem says that let epsilon be the maximum success probability of breaking an application in the AI-ROM, then it will be at most epsilon prime plus ST over P, where epsilon prime is a maximum success probability in the corresponding p-bit fixing model. And when P is roughly S times T, then epsilon will be at most 2 times epsilon prime. And note that usually epsilon prime is much easier to bound. And also, we note that the first bond is additive, therefore works better with indistinguishability game, and the second bond is multiplicative, which works better with unpredictability games. Okay, and that's the recap of the classical theorem. And now let's switch to the quantum world. So in a quantum world, random oracles are the same, which is the random function drawer at the very beginning of the game. The only difference in the interaction between algorithms and random oracles. Since the quantum algorithm can always implement a practical hash function, for example, SHA-3 on its own devices, Therefore, it is natural to assume it makes superposition queries to the random oracle. And it's also natural to define auxiliary input quantum random oracle model. Well, both the offline and the online algorithms are quantum, and the advice can be either quantum or classical. And in this work, we're particularly interested in the case where the advice is classical and the online algorithm is quantum. And therefore, as we have seen the simplicity and tightness of pre-sampling techniques in the classical setting, we ask the following question: can we leverage pre-sampling techniques to the quantum setting? And in this work, we answer this question in 3 different aspects. First, we realize that a so-called direct leveraging is difficult. We show that if such a direct leveraging would work, then it implies the famous Arison-Ambani's conjecture is true. The conjecture asserts that any quantum algorithm on unstructured inputs can be approximated on most inputs by efficient classical algorithms. The conjecture is still quite open, and the best known bound is still exponentially far from conjecture. Therefore, we think it is a barrier. And faced with this barrier, we revisit the pre-sampling techniques in the classical setting. We find that there is a much simpler proof for the previous pre-sampling theorem, which we redefine Bitfixing random oracle model and work out a simpler and a unified proof with only standard concentration bounds. This proof gives tight theorems of previous works for both AI random oracle model and AI random permutation model. And this is why we also call it a unifying approach. And with this new definition of Bitfixing model, we adapt it to the quantum Bitfixing model. And we show that with this new definition, we can prove a quantum version of the pre-sampling theorem. And further, it is optimum in the sense that it matches the classical, the parameters in the classical bound. And finally, we show the simplicity and generality of this theorem by reproving previous bound and also giving the first post-quantum non-uniform security of a Merkle-Damgard hash functions. And I guess that's everything I want to talk about today. There are a couple of technical things, but we can talk about that in the question session. Yeah. And thanks for your attention. Yeah.
So, thank you, Chipin. And any questions from the audience? There are no questions on the Zilip chat as well. So maybe if I can ask a quick question, Chipin. Do you think these ideas, these pre-sampling ideas could also be, okay, so you right now apply these ideas to prove pre-sampling theorems for random oracles from hash functions. But yes, what about some other oracle functions? Could be like some cryptographic oracles that you want to say, okay, hey, I have like pre-processing access to these oracles, cryptographic oracles. Could be an encryption scheme, could be a decryption scheme, and eventually sort of just say, okay, hey, I'll give you some polynomial twice string, and then ask the same questions. Can the techniques
I'm not 100% sure, but currently I think for these idealized models, we can generalize it, although we don't know if there's a tool to prove it. In other words, like we're going to prove security in the Bitfixing model, but then if you're caring about like other models, then you need to bound the security in the Bitfixing of other models, which I'm not sure if that's easy or hard, but there's like a natural generalization, and you can adapt this whole framework into other oracle models. But I'm not sure whether argue this epsilon prime is easy or not.
Okay. But won't the arguing epsilon prime in those cases be similar to arguing that, like here, epsilon prime is sort of arguing about the number of queries, or it's like for each random oracle query, arguing some properties. But that one is arguing the. Yes.
So this so-called Bitfixing model would you need to argue security in the Bitfixing model, and that makes some difference, and that makes things like non-trivial, I guess. Yeah.
Okay. Yes. Thanks, Shubhang. And I would say there were some questions on the Zilip chat for Neil, but I would say we can get to all the questions if we have time towards the end of the session.
Of course,
let's proceed to the next talk.
And I will look at these questions also.
Yeah. So Reo, Neil, Shubhang, yeah. It's going to be great to have you to participate in the session as well.
Mhm.
So let's move on to the next talk. And the talk is on relationships between quantum incipient notions. And Hassan, could you please share your slides?
Yes. Is that okay now?
Yes, could you start slideshow?
Yes. Is that fine?
That's great. So, okay, so the next talk is by Hassan, and the talk is on relationships between quantum incipient notions. And the paper is by Vincent Carsons, Hassan Ibrahimi, Jalal Noel Tabia, Dominic Unruh. And please correct me if I said someone's name incorrectly, but yeah, take it up, Hassan.
That was great. Thank you for the introduction. And the full version of the paper is available at EPRIN if this presentation is really short. So I will go quickly to the setting that we consider here. We're talking about the post-quantum security in the superposition access model, when the quantum adversary basically has a quantum access to the classical cryptographic construction. In this talk, we are targeting how to define the CPA notions in this model. So basically, the question is how CPA notion can be defined when the adversary may have a superposition access to the encryption scheme, and what is their relationship between the notions that have been defined. So to define such notions, we have to fill in these question marks, that how adversary interact with the challenger, and in the learning phase and in the challenge phase. And the challenge phase is colored by the red, and the learning phase or color, they don't have a color. So first, I quickly go through the existing CPA notions before our work. So there is a Boni-Azani's definition that they consider like a standard oracle access to encryption in the learning phase, and classical access to the encryption in the challenge phase. So in the challenge phase, basically the challenger, after getting two messages, it returns one of the encryption of one of the message based on the random bit of B. So this we call it the one ciphertext return. Actually, there's another definition that they consider different query model. It's called the minimal query model in the learning phase and in the challenge phase as well. So the challenge phase here is quantum, and giving two quantum states, row 0 and row 1, the challenger gets back the encryption of row B. The third notion is they consider real or random type, return type in the challenge phase, that basically the queries are implemented as a standard oracle access to the encryption scheme. So this phase are included as this. And then in the challenge phase, the challenger either apply a permutation before encrypting, or it doesn't apply. And the adversary's goal is to detect if this permutation has been applied or not. So now the question remains, are these all possible notions? And the answer is no, if we systematically want to answer the question. So I will go quickly through the options that we have. So for the query models, we have 4 options to consider, like the classical query, or standard query model, or embedding query model, or minimal query model. Embedding query model is different, a bit like slightly different from the standard query model, in which the output register here is set to be 0. So the adversary doesn't have a control over an output register. There's also a different return type, specifically in the classical case, we have 2 different notions for this, that the challenger returns 1 ciphertext or 2 ciphertext, or real or random return type. So, well, in the classical case, these notions are all equivalent. And there are a number of queries that we have to consider. There is a 0, 1, or a polynomial number. So now if we quickly do the math, then we can see that in the learning phase, we have 5 choices. And then in the challenge phase, we have 2 times, 4 times, 3 choices. And in the total, we have 120 choices to define such notions. And this is a huge number of notions. That's really frightening to want to study these notions. And so here we excluded some notions. We excluded the notions that they have different quantum queries in the learning and challenge phase. These are 36 notions. Also, we excluded the one-time in CPA notions. That is, well, basically there is one challenge query only, and then there is no learning queries. So this is the 12 notions. And also there are some notions that are impossible to achieve. It means that like any encryption scheme will be insecure in these notions. So if we do the math, we can get a 57 encryption scheme, like the security notions. Still, it's a huge number of notions. And one example of such a notion is that we consider, for instance, the minimal query in the learning phase, and then in the challenge phase, we consider real or random return type. So the notion can be defined straightforwardly, basically. So these are new notions by the combination. So we studied these notions and we grouped them into the 14 panels. And we also study relations between these panels. So the equivalent notions are grouped, and we have this table as a result. And so you may see some red non-implication that they left as a conjecture and some question mark. If we assume that we leave the red non-implication as a conjecture because we believe that this direction is more likely to happen. And if it does, I mean, if we can prove formally that it does, then all the open questions will be resolved and the table will be complete. So that's really pleasant to look at them. Also, at the end of the paper, we have a discussion related to this. So the conclusion is of the talk is we have 2 notions that implies all other notions. And this is when we consider a standard query model with the real or random return type, or minimal query model with the one ciphertext return type. We also we present a scheme that is secure respected to both these 2 notions. And since these notions together imply all other notions, then basically we have a scheme that's secure in all the possible 57 notions that we consider. And also we saw that these 2 definitions are not comparable. And this is opposite to classical case that opposite to the classical case, basically different quantum CPA notions may not be equivalent. But in the classical case, we know that all of them are equivalent. And I guess that's the end of my talk. I was fast, but I guess I'm on time. Do you have any questions?
I don't think we have any questions from the chat yet. So the chat and any questions from the audience. So just to sort of understand the contributions to this work. So do you think these 2? What do you mean by they're incomparable? Are there schemes that are secure as per definition 1, but not as per definition 2, and the same goes in the reverse direction?
Yes, exactly.
Okay.
So we cannot relate them together.
But you have schemes that are secure as per definition A, but not as insecure as per definition B, and same the other way around. So that's the case.
Yes, exactly.
Okay, and do you think a similar systematic study will be required for quantum in CPA notions, in CCA notions, chosen ciphertext attacks?
Well, for the CCA notions, there is basically there's the main challenge to define the CCA notion is when we consider the challenge queries be quantum, then we don't the challenge basically we don't have a way to record this quantum queries, and then later the decryption basically return perp or garbage when the adversary submit this query. So the recording for general encryption function, general randomized function, is not yet developed. So there's only one definition. There are some attempts to define the CC nation with the challenge queries to be quantum, but still there is not immediate success on that. So I'm afraid that defining the CC notion with the quantum challenge phase is challenging itself.
I understand. So the question was, do you think the lessons that you learned from this work about definitions about quantum in CTA notions, the similar lessons could also be used when one will be studying the CCA counterparts of all these things? Assuming, suppose we have like a starting definition where the decryption oracle query access has been modeled in an appropriate way.
Sorry, it was a bit interrupted, so I couldn't get the last few.
I think it's just maybe we can take it offline. It's not a very important question, but yeah, thanks a lot for the great talk.
I'm sorry, I didn't hear it.
Yeah, I think we just have one more talk, and we can sort of circle back to all the questions for all speakers towards the end of the session. Thanks again, Isan, again for the talk.
Thank you.
Can you share your slides?
Yes, into that. Okay, just a sec.
Okay, yeah, we can see it. So now we're on to the last talk of this session, and it's work on classical binding for quantum commitments. And it's a work by Nir Vitansky and Zvika Vrigorski, and Nir is going to present.
Okay, thanks, Vishal. All right, so this is work with Zvika, and it's about commitments. And as you all know, commitments are one of the most basic crypto primitives. They involve a sender and the receiver that interact in two phases, right? In the commitment phase, the sender commits to a message M, and in the opening phase, it can open this commitment. And the basic properties that we ask for are hiding, which means that before the opening phase, the committed message is hidden, and binding, which says that a commitment can only be opened to a single message. And in this work, we're interested in quantum commitments. Specifically, we're still thinking about committing to classical messages, but the communication and the parties are quantum. And as it turns out, for quantum commitments, the question of binding becomes rather complicated. In particular, the classical notion of binding is generally considered impossible due to a simple superposition attack. So you can think about running the honest sender in superposition over distinct messages, let's say 0 and 1. And in this case, assuming that the receiver is unitary, the message bit is not really fixed after the commitment. In fact, it can be open to a uniformly random bit. Now, of course, there does seem to be an easy solution here, which is for the receiver to just measure the entire channel, the entire commitment, and therefore effectively make it classical. And this indeed works, at least in the statistical binding setting. So what is the catch? So the point is that by forcing the commitment to be classical, we might be missing out on features that can only be achieved quantum. And one known example of this, where quantum commitments are really superior to classical ones, is that they can be constructed non-interactively from one-way functions, quantum secure one-way functions, of course. And this is not known classically. As a matter of fact, there are black box barriers for this. However, the corresponding quantum commitments are at the same time also inferior to classical commitments. For once, they satisfy a weaker binding guarantee. In particular, the committed message is not really fixed. They are subject to this superposition attack. And this also makes them harder to use and harder to analyze. And the question is whether this price is really necessary, or perhaps we can get the best of both worlds. So in this work, what we show is that the answer is essentially yes, we can achieve the best of both worlds. And let me tell you about each of the contributions. So we first define classical binding for quantum commitments, which has a similar guarantee to classical commitments. In particular, the commitment fixes the message. And intuitively, the notion we introduce can replace classical commitments in applications without really changing the proof. And we demonstrate this, for example, in classical zero-knowledge protocols. Then we show that we can achieve a statistically binding version of this notion non-interactively from one-way functions, okay? So indeed, we get the best of both worlds. Finally, we also explore a statistically hiding version of this notion, and there we show that actually classical binding is impossible. Now, I have very little time, so I will only tell you what is sort of the basic idea behind the definition, and then the idea is actually very natural. So basically, our receiver during the commitment phase is only going to make a partial measurement. And the rationale is that we want this partial measurement to be such that on one hand, the commitment will turn classical enough for fixing the message, but on the other hand, it will remain quantum enough to achieve the superior features that we're after. Okay, so let me also tell you just in a nutshell about our construction of these non-interactive commitments from one-way functions. And the construction basically de-randomizes Naor's commitment scheme, which, as you may know, is a two-message commitment. And specifically, the basic idea is to have the sender send in a single message a superposition over all receiver messages and corresponding sender messages where we derive the sender's messages in some appropriate way, specifically using a pairwise independent hash function in order to derive its randomness. Now, we're going to take this de-randomized building block and repeat it in parallel many times. And in our commitment phase, the receiver is going to measure some random subset of these commitments, and these are meant to be Naor commitments that fix the value. And in the opening phase, we're going to use the rest of the commitments in order to test that the actual commitment that the sender sent originally was well-structured or close enough to well-structured. Yeah, so this is the idea, of course, that analyzing this is tricky. These commitments are entangled, but you can watch the longer talk where we discuss more details. So I'll end here. Thanks.
Thank you very much, Nir. So any questions from the audience about this YouTube chat? I guess not right now. So Nir, this is seems like a very cool trick. So do you think this idea can also be used for sort of this sampling trick could also be sort of some other primitives? Because this seems like a very, I mean, abstractly, it seems like a very general idea.
Excellent question. So it's an open question, and we've been thinking about it, and we don't have any good answers yet. So I invite you to think about it as well. You know, perhaps like a natural candidate is, for example, zaps, right? Like turned
exactly, precisely.
Non-interactive distinguishability. Yeah. One essential difference is that zaps don't have like an opening phase. Yeah. And we're using here the opening phase where there's no secrecy left whatsoever in a very strong way. And that is the barrier there. I don't know, maybe there's a way to circumvent it. It's an excellent question.
Mm-hmm. Wonderful. Okay. So if there are no questions, thanks a lot, Nir, again, and all the speakers of this session. So I would, thanks, Nir, also for answering the question, answer the question on the YouTube chat. So at this time, we would like to invite anybody who would like to ask a question to any of the speakers in the session. And so maybe I can sort of circle back to Reo. Reo, if you're still around, I had like a quick question for you.
Yep.
So do you think the quantum lightning schemes, they were initially proposed as an interesting abstraction to build quantum money as well, and sort of applications towards quantum money. So you have like an interesting weakening of quantum lightning. Do you think you might be able to sort of also get maybe not public or public key quantum money, but with very weak unforgeability property from these ideas, because your quantum lightning scheme only relies on classical assumptions or only on sort of learning with errors and other standard assumptions. Can you use these ideas to also build quantum money schemes, though not fully public key quantum money, but only for a very restricted class of forgery attacks?
Yeah, it may be possible, but I don't have a good idea for now. So yeah, it's a good open question to find another application of this idea, like two-tier something. Yeah, like maybe two-tier quantum lightning might have some another application. So yeah, but I don't have any good idea so far. Yeah.
Okay, thank you. And just one more follow-up to your talk. It's just I think relied on, and also the other the current work relied on the ideas of watermarking, software watermarking as a particular primitive to sort of classically commit to the or classically watermark the circuit. So, but I think the ideas over there used were the original definitions of watermarking. Do you think there has been recent work in which the notion of watermarking has been strengthened to traceability properties, that those particular traceable primitives can also be used to prove certain stronger properties about software leasing if we use those particular ideas?
Oh, sorry, I didn't get your idea. So,
So I'm simply asking, currently, when you're using watermarking inside your schemes, you're using the watermarking definitions that were defined for the unremovability claims. Recently, there has been a push to sort of move from watermarking to traceable primitives, where you can have like stronger properties. So do you think if you sort of rely on traceable primitives, then you might be able to prove even stronger properties about the resulting software leasing schemes? Or do you think maybe are more fundamental gaps if you want to sort of strengthen them further?
It's a very good question. So I also tried to extend our idea to some traceable primitive, but one obstacle is we in the so secure software leasing setting. The rest use only secret key, and so the rest cannot use secret key. So it is a bit. I think it is a problem to extend our idea to tracing primitive, but I'm not sure whether it is a fundamental obstacle. So. Maybe we can overcome the issue, and we can achieve some tracing version of the primitive. So yeah, it's a good open question, I think.
Great. Thanks a lot, Reo, and thank you, Reo, Nir, Chepang, Hassan, and all of you for sort of being here.